All right. So we're going to be using this chart. Keep that handy. Okay. Let's get into it. Pull up the next section of slides. Shapes, VSEPR theory, and molecular polarity. So the last chapter was all about how to draw the right structure, connect everything, figure out how many single double bonds there are, all that stuff. But the problem is the way we've been drawing these molecules on a two-dimensional piece of paper. And what you have to remember is that molecules make up matter, which is what makes up three-dimensional space. These molecules live in three-dimensional space too. And it's easy to lose track of the fact that molecules are three-dimensional when you're always drawing them on a two-dimensional piece of paper. So molecular geometry accounts for the fact that molecules have a shape that's 3D, not 2D. So the idea here, this is called VSEPR theory. VSEPR is an acronym. It stands for valence shell electron pair repulsion, VSEPR. And it's a pretty simple theory. The theory essentially states that lone pairs take up more space than bonds, and that is going to distort bond angles when we get into some of these shapes. Okay, so let's get started. Pull out that VSEPR molecular geometry, and we're gonna get talking about this. Let's talk about this chart. So this table, yeah, sorry, you're gonna have to memorize a lot of this table, not the whole thing, but a lot of it. This table is going to tell us how to draw our structures. Okay, going down the side, this has it labeled as steric number. That is the old term that we used to use, like when I was in school. By the way, this is the exact VSEPR sheet that I learned from when I was in high school. So that's why I went back and found it, because it's fantastic. Okay, yes, I'm sure I'm biased. Anyway, we used to call this steric number back in the day. But now we just call it the electron domain. So the electron domain. And then across the top, so the electron domain, let's talk about the electron domain first. The electron domain tells you how many things are coming off the central atom. So this comes from a branch of mathematics called group theory. So for the atom in the middle, they use an E. Don't worry about that. But how many things are coming off the E? The thing could be a bonding group, or it could be a lone pair. So you can see that in electron domain 2, we have two bonding groups. You can see in electron domain 3, we have two options. We could have three bonding groups. That's three things coming off the central atom. Or we could have two bonding groups in a lone pair. That's also three things coming off the central atom. In domain 4, we got four bonding groups, three bonding groups, one lone pair, two bonding groups, two lone pairs. They all have four things. So hopefully you can see how that domain is working. Across the top, this is how many lone pairs are on the central atom. So how many lone pairs are coming off the central atom? Everybody in this column, no lone pairs coming off the central atom. Everybody in this column, one lone pair on the central atom, two lone pairs, three lone pairs, four lone pairs. You can essentially cross off this shape and this shape. We are never going to do either of those shapes. So the domain 6 T-shaped and domain 6 linear, there are very few molecules that have that shape. We're not going to get into that. But we're going to cover the rest of these guys. So best way to do this is to probably just start drawing them. So let's do it, man. Here we go. Uh-oh. Okay, a lot of times, so you should have that VSEPR sheet out in front of you. A lot of times people need to draw a bad Lewis structure first and then fix it. Like think about that table. Oh yeah, it would have this shape, and then draw the correct Lewis structure. So I'll show you what I mean. So these can take time. People can get frustrated because it can be a lot of work, especially when you're first starting out. You don't have that VSEPR sheet super duper memorized. So let's try CO2 first. before we can figure out its shape in 3 dimensions, we have to draw its Lewis structure. So I want you to take a second and try to draw the Lewis structure for CO2. All right. So here we go. We got 4 for the carbon, 12 from the oxygens. That's 16 electrons. Carbon in the middle, 2 oxygen, used up 4, got 12 electrons left. 2, 4, 6, 8, 10, 12. Uh-oh, it's a double uh-oh. What are we going to do? You need to add 2 bonds. Best way to do it, 1 on each side. Carbon dioxide looks like that. Now, so take a second. Did you draw that? Now we need to apply the VSEPR theory to this. Talk about its name, its shape, how to draw it, what its angle is. How do we do this? We always look at the central atom, and we want to know how many bonding groups does it have and how many lone pairs are on the central atom. Now, bonding group, it doesn't matter if it's single, double, or triple. That just counts as 1 bonding group. So this CO2 has 2 bonding groups, no lone pairs. So 2 bonding groups, no lone pairs. 2 bonding groups, no lone pairs. This is a linear molecular geometry. Now, this one is pretty darn obvious, right? It's linear. Obviously, the angle of a line is 180 degrees. So this is a linear shape, and it's got an angle of 180 degrees. That's my structure there. Okay. Next up. We're just going to try to march through that VSEPR chart. I have some structures here I'm going to grab in a second. NO2 minus nitrite. We did it earlier tonight. It's a resonance structure. Good review. See if you can't do it. And then we'll talk about how to draw it correctly. I'm going to grab my model kits. Hopefully you did that. Hopefully you did something like that. You found out you're short 2 electrons. I can put them on the left. I can put the extra bond on the right. It's a resonance structure. There we are. Done. Right? Wrong. You are not wrong. And this is where people start to get super angry, right? Because most people don't like resonance. And now what I'm telling you is you did all this work and you need to redraw it because this is wrong. Why is it wrong? Let's talk about that. My central atom is in domain 3. It has 2 bonding groups. It's got a bonding group here and a bonding group here and a lone pair. So I've got 2 bonding groups, 1 lone pair. 2 bonding groups, 1 lone pair. We need to find that on our VSEPR chart. So we're domain 3, 1 lone pair. That's got a bent or angular molecular geometry. Here in the States, we tend to say bent. Okay. In the United Kingdom, England, they say angular. We tend to say bent here. So it says bent molecular geometry. Okay. And the angle is going to be less than 120, which we'll talk about in a second. So you actually have to redraw this as bent. So I know. People get so angry. Don't get angry. Just do it, It's okay. Not in a straight line. Got to draw it bent. Got to draw it bent. That is how we should draw it. It's got a bent molecular geometry, bent, and it's got a bond angle of less than 120 degrees. Let's talk about why this is less than 120 degrees. And what's going on here? Well, okay, actually, we'll come back to that bond angle here in a second. We're going to draw a trigonal planar, okay, first with 120 degrees. But what's happening here is the lone pair actually takes up more space and smashes the whole thing down. So if you'll remember, we go here to the sheet. Lone pairs need more space than bonds. So if this was a perfect bond, it would be 120 degrees. Okay, but that lone pair is smashing everything down, so it's less than 120 degrees. Let's look at domain 3, 0 lone pairs, and let's talk about why that's a perfect 120 degrees. And we'll do an easy one here. Well, no, I'll tell you what, we'll do a decent one. Let's do COH2. You did this one earlier tonight, but you probably won't remember, and that's fine because we're drawing a whole lot of Lewis structures. Why don't you try and draw the correct structure for COH2? Then why don't you try to find it in the VSEPR sheet and see if you drew it correctly. If not, we'll redraw it. So try to draw the right Lewis structure first for COH2. And then we'll talk about how to draw it correctly. All right. We got 4 plus 6 plus 2 equals 12. Carbon in the middle. 2 hydrogens coming off of it. Used up 6. Got 6 left. We're short. That's an uh-oh. You got to add a bond. Only place you can add it, and I'm drawing this intentionally bad, is here. So up until 5 minutes ago, this would have been totally fine. This is the correct Lewis structure. But this is not the correct molecular geometry. Let's talk about why. Central atom is in domain 3. There are no lone pairs on that central atom. So we're in domain 3. We got 3 bonding groups, no lone pairs. This is going to look like this. This has a trigonal planar molecular geometry with bond angles of a perfect 120 degrees. Why are the bond angles a perfect 120? Because there are no lone pairs, and lone pairs need more space than bonds, so they're not going to push the bond angles apart. It's going to be a perfect 120. So here's the problem. If I ask for the molecular geometry and not the Lewis structure, this is not okay. You got to redraw this. We need to redraw this with angles of 120 degrees. So double bond, hydrogen, hydrogen. You should have a 120-degree bond angle here. Think about it. That should make sense. If this is a circle and you chop it up into 3 equally sized slices, that's hard to say, it would be 120 degrees for each one of those slices. So trigonal planar. Trigonal planar. Why do we call it trigonal planar? Great question. I will show you. We call this guy the trigonal planar molecular geometry because all 3 atoms in a trigonal planar molecular geometry are in the same plane, right? We got a perfect 120 degrees, and all 3 of the atoms are in the same plane with one another. They are all in the same plane. So it's a triangle, boop, 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 right? It's a triangle, and all the atoms are in the same plane, trigonal planar. That's where that shape comes from. So the first 2 domains are not too bad. Domain 2 is just linear. Domain 3 has trigonal planar. And then if you replace one of these with like a lone pair, so if I have a lone pair, I'll just use this as my lone pair. Here was my nitrite. If I get a lone pair sticking out of it, that's going to be a bent shape, and it's going to smash everything down. It's going to be less than 120. Those shapes are not that bad. Domain 4 is where things start to get more complicated because you've got to show 3-dimensionality now in domain 4. So let's talk about domain 4. And domain 4 is where I think the VSEPR, the fact that lone pairs take up more space than bonds, I think is where it really starts to make sense. So let's just do CH4. Let's keep it simple. So go ahead and draw the Lewis structure for CH4. So hopefully you drew something like this. 4 plus 4 equals 8. Carbon in the middle. 4 hydrogens coming off of it. Hopefully you drew that. And on 7 minutes ago, that was cool. Now, no longer cool. This is where it starts to get more complicated. If we lived in a two-dimensional reality, that would be CH4. But we don't live in 2 dimensions. We live in 3 dimensions. So those 5 atoms, because there's a carbon in the middle, okay, or those 4 bonding groups can get further apart than 90 degrees. In 2 dimensions, the furthest they could get apart, excuse me, would be 90 degrees. But in 3 dimensions, they can get further apart than that. Okay, and the answer is they can get 109.5 degrees apart. What we end up with is domain 4 zero lone pairs, which is the tetrahedral molecular geometry. But now we need to draw this in 3 dimensions. And now the way we're going to do that is use wedges and dashes. So here is how we draw a tetrahedral molecular geometry. The bond angle, and you're just going to have to memorize this bond angle, is 109.5 degrees. This chart only has 109. That's fine if you don't put the 0.5, but I'm telling you it's 109.5. So we're going to draw one of the bonds in the plane of the paper. And then, over here we have a wedge. This would be the atom that's like coming out at you. And then we have a dash. This would be an atom that's going back into the board. Now, every single bond angle here is 109.5 degrees. Okay, so that is how it would look. Now, before we draw this, let me show you a tetrahedral CH4. Here's what we have. This is what methane looks like in the real world. So if we look, here are the 2 bonding groups that are in the same plane. Okay, so these guys are 109 degrees apart. And then we have one coming out at you, that's the wedge, and there's one going away from you back here, that's the dash. So how do we draw this? Okay, well, you could draw any one of the 2 like mirror images. So we got a carbon. You could put these 2 in the plane with an obtuse bond angle of 109.5 degrees. Okay, so essentially I just like shifted that guy down. And now another hydrogen needs to be coming out at you. We show that with a wedge. And another hydrogen needs to go back into the board. Now the way we show that is with a dashed line. Like that. I don't like that either. There we go. So that's how we show that. All these bond angles are 109.5, and it's a tetrahedral molecular geometry. Now, you could draw the mirror image. Okay, this would be totally fine to draw as well. You could put the 2 hydrogens in the same plane on the left side, and then you can wedge this guy coming out at you, and dash this guy going away from you. So it doesn't matter how you want to draw it. Both tetrahedral, okay? And domain 4 is where you really now have to start to try and attempt to have at least some kind of artistic skill, because we're trying to show 3 dimensions. Everything isn't all in the same plane. Okay, let's do the next one in domain 4. Try NH3. Give that guy a shot, and we'll talk about how to draw it correctly. All right, so we draw a crappy Lewis structure. 5 plus 3 equals 8. Nitrogen in the middle, 3 hydrogens coming off of it. We're going to pop a lone pair here on the nitrogen. But this is not an accurate description of what it looks like. This is a valid Lewis structure. It is not the correct molecular geometry. If we go to the VSEPR chart, this is domain. So first of all, this is domain 4, 3 bonding groups in a lone pair. There are 4 things coming off that central atom. 1, 2, 3, 4. One of them is a lone pair. So we're in domain 4, and we have 1 lone pair. Domain 4, 1 lone pair is a trigonal pyramid. How do we draw it? Lone pair at the top. It's like tetrahedral, but we replace it with a lone pair. Now, we do not need to show lines to our lone pairs. This table does that to emphasize where the lone pair is, but we do not generally do that. So the way that we're going to draw this is we're going to keep the lone pair right on the nitrogen. We're going to have this guy be that next to it in the plane. And then we have one coming out at us and one going away from us. Now let's talk about the angle. If you have tetrahedral, if you replace one of the bonding groups with a lone pair, here's what's happening. This was my tetrahedral. This was my CH4. But now I've replaced one of the bonding groups with a lone pair. The whole point of VSEPR theory is that lone pairs need more room than bonds. So what's happening here is this lone pair smashes these bonds down. In a perfect tetrahedral, all the bond angles are 109. But when I replace one of the bonds with a lone pair, it smashes it all down, and now I'm less than 109.5. Less than 109.5. So this bond angle here is now less than 109.5 degrees. VSEPR theory, valence shell electron pair repulsion. Electron pairs take up more room than bonds. So that lone pair up here is smashing that all down. All right, cool. Let's do our next shape. Very important shape. Let's do a water. Go ahead, draw a Lewis structure for water. And if you had high school chemistry, high school biology, you might draw. So when we draw water, 2 plus 6 equals 8. Hydrogen can't be a central atom. And I'm going to draw this terrible on purpose. There's our Lewis structure for water. Domain 4, because we got 4 things coming off the central oxygen atom, 2 lone pairs. Domain 4, 2 lone pairs, right? Okay, so how are we going to draw this now correctly? Well, domain 4, 2 lone pairs, let's look it up. Domain 4, 2 lone pairs is not linear. Domain 4, 2 lone pairs is going to be bent or angular like this. Okay, and you'll see here, it's not a typo. There's 2 less than signs. It's much, much less than 109.5, which we're going to talk about. So here's what's happening. Okay, you need to show the hydrogens down like this, and there are 2 lone pairs. Now, if you look at the VSEPR chart, they wedge and dash the lone pairs. Okay, coming out at you, going away from you. You don't need to do that. Okay, because lone pairs, you can just stick them right on there. So here's what's happening now. We are now taking our tetrahedral molecular geometry, and we're going to replace 2 of the bonding groups now with lone pairs. So I'm going to leave the bonds, but take the atoms off. So we have this. And we have, see the lone pairs on the top. Now, here's a nice thing. These 3 atoms are all in the same plane, which is why you can draw it like that, right? Because they're all in the same plane. And one of the lone pairs would come out at you. One of the lone pairs would be going away from you, but you don't have to show the wedge and the dash unless you really want to. Now, what does this do to the bond angle? Well, because there are 2 lone pairs, they are sticking out here. They really smash the bond angle down. Like it gets smashed way, way down. That bond angle goes from being a perfect 109.5 to much, much less than 109.5. So this bond angle is much, much less than 109.5 degrees. Much, much less than 109.5. Woo! That gets us through domain 4.